observations for perfect problem 4 for Math 243. The basic idea here, I was trying to illustrate the central limit theorem, which I said to illustrate the central limit theorem. And the basic idea is we have 3 different lists here. And the first lists are just 30 observations. Sorry, there's so many. Taken from some population. What you'll see is, as this data shows, is that population is very right skewed, or at least this data here is right skewed. List B and List C are a little bit different. List B is similar to List A. It comes from the same population. And the only difference is, instead of just taking single observations from my population, I took pairs of observations. So over here I just took a single observation. 1 was an observation, 2 was an observation, 2 was an observation, so on. Over here I took pairs. So 2 separate observations, added them together, divided by 2, and that gave me 11. I did that again. So each one of these observations is a sample of size 2, and it's a sample average. And then List C, it's the same idea as List B, except instead of finding a sample of size 2, I took a sample of size 10. And so this 6 right here represents 10 observations that List A comprises. And it's a sample average of those 10. At any rate, once you enter all that data, you can calculate stuff. You can, how should I do this? Maybe mean, then standard deviation, and we'll do list A, list B, list C, and maybe I'll even do a little shape here to summarize all of my findings. So you enter all this data into lists. It's probably the worst part of this entire problem. I went ahead and did that already, so you don't have to watch me type in all these numbers. List 1 is A, list 2 is B, list 3 is C. And then if you go over to stat, calc 1 variable statistics, and calculate 1 variable statistics on L1, you'll find out that the mean of this list, the sample average, is 4.6, looks like 4 2/3, so maybe I'll call it 4.67. And the standard deviation, the sample standard deviation, looks like it's 4.27 if I round it off. Shape off the weight, I'll have to look at a histogram to figure out the shape. It'll turn out that it's right skewed. You might be able to get that just from looking at the data. But I'll hold off on that. What about List B? We'll do the exact same thing. Stat, calc, 1 variable statistics, except instead of calculating them on L1, calculate them on L2. I get that the mean was 5.1 here, similar to the mean above, but the standard deviation should be very different. In fact, it's 2.68. Shape, again, we'll wait. What about List 3? Well, stat, calc, 1 variable statistics, L3. And I'll figure out that the mean of L3 was 5.0. Guess I was doing 2 decimal places, and all of a sudden I'm doing 1. Whatever. Actually, I'm going to go back and recalculate 1 variable statistics for L2, because apparently I'm running to 2 decimal places in my mean. Oh, it's 5. That explains why it was 5.10. And then as I was looking at it, we can go calculate my 1 variable statistics on L3. And we find that the standard deviation is, again, quite different. Smaller, 1.27. Mean stays pretty constant. Standard deviation changes by a lot. It turns out that that's predictable. We would have expected the standard deviation in List B to be related to the standard deviation in List A. Maybe expected, how about I do that over here? Expected standard deviation. And really we're just calculating those for List B and List C. And what they'll be equal to is 4.27, my standard deviation from List A, divided by the square root of n. So since n is 2 in List B, I divide by the square root of 2, and I get that my expected value was 3.02. Not exactly what I got, pretty close. What about for List C? Well, I would have expected that standard deviation to be 4.7 divided by the square root of n, but now since they're averages of 10, my value of n is 10. So I divide by the square root of 10, and I get this 1.35. Again, not exactly what I got, but pretty close. My expected standard deviation was close to my standard deviation. I don't know that I'm really doing these in order. I think basically what I asked you to do is figure out all this information, draw histograms, and talk about this shape. So I can do that now. I have all the data in here. I can get a histogram. Let's go to stat plot, turn it on, calculate a histogram on list 1. What should I make my bin sizes be equal to? You can do whatever the hell you want. I think I mentioned in class that a bin size of 2 might be a good idea for this first group. So let's see, my largest observation is 20. So I'll have my x's go from 0 to 22 with a bin size of 2. My y's, I don't think I have more than 10 in any bins. Maybe I do. Maybe I should go 15. I don't know. Take a look at the graph. There it is. Wow, it definitely had more than 15. So here's my list A histogram. Looks like there are just a few. I'm going to do it really roughly speaking. There are a ton. Maybe yours will be a little bit more precise than mine. And then we had a couple of gaps. And then another one. Then one gap. And then a final one. Sure. There's a really bad histogram of list A. Really all I wanted you to get from this is, oh, that's definitely right skewed. No doubt this is right skewed. Most of my data is over here to the left. I have a long tail going out to the right. Definitely right skewed. What about list B? We can figure out by going into stat plots and figuring out a histogram the same way we just did, except now instead of my values being in L1, they're in L2. What should I do as far as the bin sizes? I don't remember. I think I told you to go down to 1. It really doesn't matter what you do. You should be able to get the general shape from any bin size. But I'm going to make my bin sizes 1. And since my data, it looks like it goes up to 11, I'll have my maximum value be 11 here. Let's take a look at the graph. All right. Oh, you know what? I want to change the window. Since it goes up, I have observations up to 11. I'm going to make my window go up to 12 so I can see those last ones. There they are. Let's try to draw that histogram. Again, I'm going to do it very roughly speaking. Looks like we got nothing for a little while, and then we got a kind of tall one, the tallest one a little bit shorter than that, one a little taller than our first one. And these appear to be about the same as the first one. Get something that looks more or less like this. Close enough. Shape, I don't know. Still right skewed. Is what it looks like to me. Maybe, but not as bad. But not as much. Okay, what about list C? Same thing. Go into stat plots, and now just change the list that we're calculating the data on into L3. Let's see, my maximum observation, I see some 7s. I don't know if there's an 8 in there. Oh, there's an 8. Just to be safe, maybe I'll make my window go up to 10, just in case. And take a look at the histogram. There we go. That's looking a little bit better. Better being approximately normal. Our book wants n to be as large as 30 before it says that, yeah, all right, the shape will be approximately normal. But what you can see here is even when n is only 10, takes a parent distribution that's very, very right skewed, and already you get this pretty nice distribution. This looks pretty symmetric to me. Something like that. I would say for C here, approximately normal. Didn't quite keep these in line, so maybe this will make it better. Maybe it'll make it worse. Who knows? Wait a minute. This is all list B. This is still list B. And that's list B. And list C looks like that. Wait a minute, that was supposed to be in list C. Man, this is hard. Sorry, you probably don't want to sit here and watch me draw lines. It should look like this. And I think I've hit everything here. Maybe I'll go through and read through the problem one more time just to make sure. When I'm done making this little grid. Calculate the mean and standard deviation for A. Sure, no problem. Sketch its histogram. Got it. Comment on its shape. Looks right skewed to me. Each observation in B is the average of 2, so N is 2. Calculate the mean and standard deviation. Got those. And compare it to what you would expect it to be. Close enough. 2.6 versus 3.0. I mean, it could be closer. But it's not bad. 2.7 here is certainly closer to the expected value than it was to the 4.2 that we had from list A. And then sketch a histogram. Did it. Comment on its shape. I don't know. Still right skewed. If you said this is approximately normal, you could probably get away with that. Doesn't look too pretty to me. It looks like you still got a tail going out to the right, but whatever. What about list C? Now it's the average of 10 randomly selected observations, so N is equal to 10. Calculate the mean and standard deviation. Here they are. And compare them to what you would expect. I'd expect the mean to be the exact same in all three of these cases, and they're pretty close. But the standard deviation here is 1.27. I'd expect it to be 1.35. Wow, that's really close. My histogram, here it is. Shape this has looks approximately normal, just like the central limit theorem would suggest. So it looks like everything's working out about how it was supposed to work out. So that was kind of the purpose of this problem, so I'll end the video there.